I'm here on the northwestern coast of Turkey, on the Aegean Sea. Behind me is the Greek island of Lesbos, and I'm also about 6 kilometers from the ancient village of Assos. Now, Aristotle lived in Assos for 3 years, from 348 BC. He had a school there, and for the first time he developed his ideas about classifying the natural world. So one could say that I'm right in the philosophical and scientific birthplace of classification. But now I want to tell you my cluster challenge story. So here it is. So let's get straight to the point. The data set that was provided consists of 928 sufferers of lower back pain. They answered a questionnaire that had 112 questions. These are the so-called baseline variables to be used in the clustering of the respondents. It's a mixed bag of variables. Mostly they have categorical scales, but 8 out of the 112 are measured on continuous scales. The objective is to obtain a classification of the patients based on these variables in order to find clinically applicable and useful groups. The organizers of the challenge gave some guidelines. The number of groups should be between 3 and 12, and optionally the groups could be checked for prognostic value against an additional 9 variables representing the longitudinal outcomes after 2 weeks, 3 months and a year. The problems that have to be faced with this challenge are the following. First, the mixed scale nature of the variables. Second, there are lots of missing data. Almost 7,000 values are missing. That is 6.7% of the data. Third, a way of selecting the number of clusters is needed. And fourth, the final clusters need to be interpreted according to the 112 baseline variables used. Now I'm guessing that perhaps my approach may distinguish itself from other attempts, in that I use correspondence analysis to solve all these problems except for the cluster analysis itself. Because correspondence analysis specifically treats multivariate categorical data, it can handle the mixed scale variables, where fuzzy coding is used to pre-transform the 8 continuous variables into fuzzy categorical ones. Correspondence analysis can handle missing data without imputation or case deletion, since a missing response can simply be coded as an additional category. Finally, it can help in the final stage with the interpretation of the clusters, which just define another categorical variable. But for the clustering itself, k-means will be used. To homogenize the scales of measurement, all variables need to be categorical. Fuzzy coding converts a continuous variable to a fuzzy categorical one. In this case, 4 fuzzy categories were defined for each continuous variable using 4 triangular membership functions. This shows the case for body mass index, where a BMI of 26, for example, is converted to fuzzy categories with values 0, 0.65, 0.35 and 0. This is a precise coding of the value 26. The fuzzy coded continuous variables can be analyzed jointly with the other crisp ones, which are coded as regular dummy variables. Now the missing data problem. Missing data forms 6.7% of the data, but because all data are on categorical scales, a missing value category is simply added to the variables that need one. To avoid missing data categories dominating the analysis, a version of correspondence analysis called subset multiple correspondence analysis, or subset MCA, is used. This approach ensures that all cases can be included and no imputation is needed at all. The subset MCA generates 309 dimensions, of which the first 73 are used for the clustering. The choice of 73 is based on what's presently a heuristic for MCA, but which I have conjectured is the totality of interesting dimensions. The rule is to use those dimensions for which the corresponding variances are greater than 1 divided by the number of questions. In this case, this gives 73 dimensions. With the 928 cases now being brought into a 73-dimensional Euclidean space, that is, with all the categorical data effectively quantified, non-hierarchical k-means clustering can proceed. A series of solutions was tried from 2 up to 15 clusters, each time with 50 random starts. The left-hand plot shows the increase in between cluster sum of squares as a fraction of the total, increasing with the number of clusters, a concave function. The right-hand plot shows the increments, which are decreasing. From 7 clusters onwards, these improvements are small, so the 6-cluster solution is chosen, with 42.5% of total variance equal to the between-cluster variance. The cluster sizes vary from a small group of 47 for cluster 5 to a large group of 234 for cluster 6. In order to interpret the clusters, the complete set of 112 crisp and fuzzy categorical variables can be cross-tabulated with the 6 clusters, and correspondence analysis can be used to identify the most important variables distinguishing the clusters. The left-hand plot shows the 928 cases first in the first 2-dimensional solution, in the best 2-dimensional solution, where clusters are color-coded and 95% confidence ellipses for the cluster means are shown. The third dimension, shown as the horizontal axis in the right-hand plot, separates cluster 5 from the others. This is better appreciated by seeing a 3-dimensional view of the points and their 95% confidence ellipsoids around the cluster means. Cluster 5 can be seen separating from the others on the third dimension and has the largest confidence ellipsoid around its mean because it has the smallest sample size. To characterize the clusters, this plot shows the 2-dimensional plot of the cluster centroids and the corresponding positions of the categories of the most discriminating variables. Clusters 3 and 6 oppose each other along the first horizontal dimension. Cluster 3 being the acute sufferers of lower back pain with difficulties getting out of a chair and decreased sexual activity, contrasted with cluster 6, the less acute sufferers, still enjoying things they used to do. Clusters 2 and 4 oppose each other on the second vertical dimension, characterized by shoulder and or neck pain in cluster 4 with less than 30 days lower back pain per year, versus cluster 2 with more than 30 days back pain per year but no shoulder or neck pain. Cluster 1 consists of people with some psychological symptoms such as being irritable with people and daily life problems such as work making the pain worse. Cluster 5 is on the side of the more acute sufferers, but it is necessary to interpret its position along dimension 3, shown here again as the horizontal axis. The categories of the most discriminating variables here along the third axis indicate that in cluster 5, the smallest cluster, leg pain dominates the back pain, and the pain is from moderate to worst imaginable. So, here is a summary of the 6 clusters, showing their sample sizes proportional to the sizes of the circles. To understand the cluster demographics, this plot shows the gender distributions in the 6 clusters. There are significant differences according to the chi-square test, with females proportionally higher in the 2 smaller clusters, 1 where pain causes psychological and daily life problems, and 5, the cluster associated with acute leg pain. Females are proportionally less in the largest cluster of less acute lower back pain sufferers, that's cluster 6. The age distributions are also shown for each cluster. These are what I call confidence plots for the means. They are not box plots for the individual level data. The boxes here show 50% confidence intervals and the whiskers 95% confidence intervals. The differences are highly significant, with lower ages in cluster 1, cluster 4, those with shoulder or neck pain, and cluster 6, the less acute lower back pain sufferers. Finally, the clusters are compared with respect to the longitudinal outcomes, which were not used in the clustering. There's not enough time to go into details here, but the clusters are well separated and all show the same pattern as this one for global perceived improvement. There is a wide dispersion of improvements after 2 weeks, with clusters 1 and 5 generally showing the least improvement. Note that high values equal less improvement or the worst cases. After 3 months, all clusters improve more, but then there is a slight worsening after 12 months. This is seen similarly for lower back pain intensity, but the 12-month intensity values here are similar to the 3-month ones, and also for the Rowland-Morris scores. The main point to note here is that the clusters are well separated on these outcomes. Well, I hope you like my story and my approach using correspondence analysis, which is perfectly adapted to multivariate categorical data. So now